Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today I'm joined by Dr. Andrew Knoll. He is the Fisher Professor of Natural History at Harvard University. His research focuses on the early evolution of life, Earth's environmental history, and especially the interconnections between the two. And today we're going to focus on his book, A Brief History of Earth, 4 billion years in 8 chapters. So, Dr. Knoll, welcome to the show. It's a pleasure to have you on.
Thank you. I look forward to our conversation.
Where does this history really start? Because, with the formation of the Earth and all of that, what would you say, for example, are the chemical elements that played the most important role in the formation of the Earth?
Okay, well, it turns out the answer to that depends in part on what part of the Earth you're interested in. If you look at the solid Earth, the rocks beneath our feet, then the most important elements are silicon and oxygen, which are usually bound together. That's what quartz is, for example, but also iron, magnesium, calcium, things like this. And that makes up most of the composition of the rocks of Earth. Now, what's interesting, of course, is that the fluid Earth, the oceans, the atmosphere, are very different. That's, mostly water, and then in the atmosphere, mostly nitrogen, some oxygen gas, and a little bit of carbon dioxide, which plays an outsized role in regulating climate. And then, of course, there's us. Life is substantially based on carbon, with important supporting roles for hydrogen, oxygen, sulfur, phosphorus, nitrogen, things like this. And the important point is that all of those materials, whether you're in the solid, fluid, or biological Earth, accreted as part of the Earth as it formed.
And how did the Earth form exactly? What were the main steps?
Well, the main thing, and this is true, I think, of all stars and the solar systems around them, is that our history began, say, 5 billion years ago, with just a nebula, the kind of thing we see in telescopes where there is a local concentration of gases and dust and things like this, and then perhaps nudged by a nearby supernova, an exploding star, that nebula began to contract. And as it did, gravity made it contract even more. And so over some interval of time, most of the material that was in that nebula ended up in the sun. But there was a disk of dust and ices around it. And again, it turns out gravity is basically the sculptor of the universe. And in this case, some of these particles would hit together and stay together. Now they have more mass, so they will attract others. And on a relatively short time scale, probably a few million years, that sort of disk of dust and ice condensed into about 8 planet-sized structures, plus a lot of other materials that give rise to meteorites and things like this. So basically, the Earth, the script for the formation of our solar system seems to be a fairly general one. And actually, with the kind of telescopes we have now, we can actually see, new stars and their planetary systems forming. And that gives us some confidence that our view of the Earth is broadly correct.
And how and why did the Earth and other planets, for that matter, take this particular shape?
Well, that's a good question. And one of the questions is how many different shapes are available? Until well into my professional career, the only solar system we knew anything about was our own. Now that we have ways of looking at, planets around other stars, we see that there's a lot of variation, and it's not clear that there's anything unique or representative about our own solar system. But in general, I think all solar systems begin in the same way. They all use some combination of the same elements. And those elements are actually formed in stars billions of years ago. So there are no new elements forming when the Earth forms. We're using things that were spewed out of dying stars, many billions of years ago.
Mhm. And how did the Earth become layered? How did the layers form, basically?
Yeah, it turns out that as the Earth accretes and gets larger, there are two sources of heat. One is just the heat of impact, because as larger and more materials bump into the Earth,
Mhm.
there is a heat transfer there. And then early in the history of our solar system, there was a fairly high concentration of radioactive elements, things like uranium that give off heat as they break down into lead. And so between those two, the Earth basically melted. And the very heavy materials, mostly iron, went down into the center. That forms the core. And then around that was this large layer called the mantle, which is mostly made up of these minerals made with silicon and oxygen. And then through time, parts of the mantle differentiated to accumulate at the surface. And that's the very thin layer, the crust, which is the only part that we see around us on a daily basis.
Mhm. And how did it get its atmosphere? I mean, how did it develop to begin with?
Yeah, again, there's a number of great questions nested there. Um, Again, all the material that's in the atmosphere arrived as part of the materials that accreted to form the Earth, and as the Earth it heats up in the interior, not only does this rearrange the rocky parts, but the lighter elements, which are sometimes called volatiles, actually degas up to the surface. So water degassed, originally probably forming a thick uh, atmosphere of vapor, and then as that cooled down, the vapor condensed into water, and we got the first oceans. So if you had been here 4 billion years ago, you would have seen a an atmosphere that was largely nitrogen, and with probably an order of magnitude or more CO2 than we have today. But there was no oxygen, and that's key. And the geologic record tells us that oxygen has accumulated through time in a series of steps. And as near as we can tell, the only quantitatively important source of oxygen for the atmosphere was actually photosynthesis. So, in many ways, the atmosphere that allows us to breathe is a product of biology.
Are we sure about where water came from?
Yeah, I think at some detailed level, there is still some debate among uh, scientists, but I would say everyone agrees that the water came in as part of these building blocks of the planets. And we're confident of that because some of those building blocks are still in the solar system and some of them fall down onto the Earth on a regular basis. We call them meteorites. And you can look at certain types of meteorites. They contain water, and it's often not liquid water. It's what a chemist would call water of hydration. That is, it's actually chemically bound to other elements and minerals. But you have water, you have carbon. There are some meteorites that are 10% organic matter, for example. So all of that material is what accretes and gives rise to the fluid and biological Earth. And the details, the arguments that persist are really about, what percent of this particular type of meteorite versus that particular type. But nobody really argues that meteorites are basically the materials from which the water came. A little bit may have come from comets, which are mostly ice, but Not that much. There are chemical reasons for thinking that meteorites are doing the heavy lifting.
Uh, and how did the plates originate? I mean, why is it that in the Earth we have plate tectonics?
Yeah, that's a great question, and it's a question that is not completely resolved. Uh, as part of the backdrop for thinking about that is that, if you look at Mars or Venus, they don't have plates. So the formation of plates is not an inevitable part of planetary formation. We know, in a sense, what drives plates in that, and that is the convection of materials in the mantle underneath the crust. But exactly why it started and even when it started is still under debate. I think we have fairly good evidence now that there was some lateral movement of crust, more than 3 billion years ago. But whether that was, identical to what we think of as plate tectonics today is not clear. So it's a question that people are still working on.
And how did we get the sort of geography landscapes that we find on the Earth? I mean, how does that uh, get created?
Well, it's a combination of two things. One is plate tectonics, and I'll say a little bit more of that in a second. And the other is erosion. That is, in terms of plate tectonics, where there are places where one plate sinks beneath another. And that's happening in the west coast of North America, for example, off the coast of Japan. And that gives rise to melting, that gives rise to mountain ranges. So that's one way of forming mountains. Sometimes two continents actually collide and we get mountains that way. That gives us the Alps, the Himalaya, and things like this. So it's actually that, the Earth's dynamic system gives rise to these elevated and in some cases depressed areas. And then erosion goes to work. I mean, the reason we have the Alps is because of plate tectonics. The reason that we have shapes like Mont Blanc and things like this is because erosion is constantly wearing those mountains away.
Uh, I think this might be perhaps one of the most contentious questions among biologists, astrobiologists, and even chemists and other people like that. So, what is life exactly?
Um, there are people who get all excited about whether we actually should have just one definition of life,
Mhm.
and if so, what it should be. I think there's two definitions that have a lot of people uh, uh, happy about. One is really more of a description. I think the only life that we know anything about, which is life on Earth, can at least be characterized as having metabolism, that is, it exchanges materials and energy with the environment, and it also grows and reproduces using those materials and energy, and it is actually separated from the environment by a membrane, things like this. So in a sense, that's a description of life as we know it. Now there's another definition of life which I really like, which says that life is a self-reproducing chemical system capable of Darwinian evolution. And you know the idea that something evolves really does separate you and me from a quartz crystal. Quartz crystals can grow, they can use up materials from the environment, but a quartz crystal that formed 4 billion years ago will still be a quartz crystal. But a bacterium that lived 4 billion years ago has given rise to all the diversity that we see around us. So I think that evolution is what I would underscore as saying what makes life different from the physical universe.
But from the point of view of chemistry, is it really possible to choose to pick a point where we can really draw a strict line between the organic and the inorganic?
I think today you can do that pretty well. Had you been around 4 billion years ago when life was just getting started, I can actually imagine that there were intermediates, some more chemical, some looking more biological, and that it was not that, you know, some Thursday life begins and is completely differentiated from the physical earth. So, like I say, today it's easy. When life was forming, it would have been hard.
And what is our best estimate for when life first appeared?
Okay. The first thing to say is that we think the Earth is a little more than 4.5 billion years old itself. The hard part about saying when life began is that as we go back in time, the geologic record that allows us to look for things like fossils and other indicators of biology gets scarcer and scarcer. And I would say the oldest sedimentary rocks where we can actually ask questions about life and be confident about what the rocks are telling us are about 3.5 billion years old. And it's very clear that 3.5 billion years ago, there was a biological carbon cycle, there was a biological sulfur cycle. So one can imagine a world of some diversity of bacteria and their cousins. There are, in some more altered rocks that are a little older, there are at least variably reliable indicators of life. But the problem with the Earth is that we have no rocks of any type that are older than 4 billion years. So what we can really say is the first time that geology gives us a peek at the past, life is already there.
Uh, are we sure about the conditions that had to be set in place for life to emerge on Earth?
Well, I guess the best way to, the most honest way to answer that is to say that most people who work on this question are sure of the answer to that question, but they all disagree with each other. So I think, there has been now 70 or 80 years of experimentation by people who are interested in this question, beginning with a classic experiment in the 1950s by a man named Stanley Miller, in which he took a beaker that had carbon dioxide, methane, hydrogen, and ammonia in that, which is what he thought the atmosphere of the early Earth might have looked like. And then he just passed a electric charge through it, which was to simulate lightning. And, within a short time of him doing that, some brown stuff started accumulating on the sides of the beaker. And there are things like amino acids in there, amino acids being the building blocks of proteins. So people have done all sorts of experiments. It's pretty clear that given the right conditions, that the basic building blocks of proteins, nucleic acids, membranes can form spontaneously. And I would say that certain types of meteorites, I talked about those that have, say, 10% organic matter in, they can have dozens of amino acids that are in there. They're mostly not the ones that are used in biology, but this shows that under the right conditions, you get the building blocks of life. Now, two final things. One is part of the right conditions is you can't have oxygen gas. If you have oxygen, this chemistry will not work. So the fact from geology that the early Earth didn't have any oxygen gas, or at least not accumulating in discernible quantities, is consistent with what the chemists tell us what you need for life. And then the final question is, does this happen in a deep sea hydrothermal vent, which some people would like that idea. Others think that a better environment are lakes, particularly lakes that might wet and dry on a regular basis. And so that argument rages, and I would simply say to those people, go to Iceland, where there are hydrothermal vents of the mid-Atlantic ridge, which are sitting above sea level and can vent into lakes. So although there's a lot of debate about this, these are not mutually exclusive environments.
About the building blocks of life, do you think that there's good evidence that all of them could have developed on Earth, or that at least some of them would have been brought to Earth from some extraterrestrial source, let's say?
Yeah, that question is another one that people have considered for a long time. I think if you want to get some of the building blocks for life on Earth from somewhere else, that just kicks the can downstream a little bit. I mean, you still need to form them in some kind of planetary or protoplanetary environment. And if you ask about Earth in particular, there's only so many possibilities of what could provide materials, comets and meteorites, particularly ones that might come from Mars, which we know some do. Um, so although I can't rule out some contribution from an extraterrestrial source, I think there's no reason to doubt that all of the major things that give rise to the chemistry of our cells could have and very likely did originate in terrestrial environments.
So, one of the big questions about the emergence of life on Earth has to do with what came first. Was it RNA or metabolism? And I mean, people call the call it the RNA world hypothesis, and on the other hand, the metabolism first hypothesis. Do you think that one has more evidence than the other to back it up, or not exactly?
Yeah, that again, that's a good question, and that's a particularly fierce debate among the people who do origin of life science. I think there's a lot of evidence that suggests that we could, by physical processes, give rise to strands, RNA-like strands of nucleic acids, that those could replicate themselves. A friend of mine at Harvard, Jack Szostak, showed years ago that you can actually show natural selection among these for function. And the great thing about nucleic acids is we tend to think about, DNA, which is kind of this inert library, but RNA is not only the scribe of our body's chemistry, but there are RNA molecules that act as enzymes, just like proteins do. So the good thing about RNA is that it can be both the informational molecule and a functioning working molecule in a primitive cell. So I like the idea that that was central. Now, having said that, it is interesting that many of the intermediates in what's usually called the Krebs cycle, which is important in modern metabolism, can form spontaneously in hydrothermal vent environments. In fact, this lake versus hydrothermal vent, you pretty much get the same people on different sides of that environmental issues, and they almost cleanly separate out into RNA people and lakes and metabolism people and the deep sea hydrothermal vents. I think the honest thing to say is that the last common ancestor of life as we know it already had both. And what neither side in this debate has been able to do is to show convincingly how the two systems merge. I think that's maybe the largest outstanding question in origin of life science.
And how was it that oxygen became one of the most common atmospheric gases?
Yeah, well, as I said earlier, the interesting thing about oxygen is there are non-biological ways of making oxygen. So, for example, there's a little bit of oxygen gas on Mars, and we think that that occurred by physical processes. But nobody has ever figured out how to make oxygen in the quantities needed to make an atmosphere that is familiar to us without involving biology. So there are many different types of photosynthesis carried out by bacteria, but the most important one for the history of our planet is what we always call green plant photosynthesis, although there's reason to think that it ought to be called bacterial photosynthesis. We can talk about that later if you like. Mm-hmm. And in that photosynthesis, basically carbon dioxide and water react to make a sugar, and the byproduct of that is oxygen gas. And so that process is necessary for us to develop an oxygen-rich atmosphere. It's probably not sufficient. In fact, there's reason to believe that the metabolism, the process of oxygen-producing photosynthesis probably predates the first accumulation of substantial amounts of oxygen in the atmosphere by hundreds of millions of years. So the trick there is a balance between how much oxygen is being produced, which is a function of nutrients and environment, versus how much oxygen is being consumed. Because all these volcanoes are, pushing out gases that can be reduced by oxygen. There are, minerals that will react with oxygen, and that. So one way or another, at about 2.4 billion years ago, the balance tips, and we develop an atmosphere that has permanent amounts of oxygen. You wouldn't have been able to breathe in that atmosphere because it was still probably only 1% or a couple of percent of the oxygen in our atmosphere, but it was enough to get new types of life going. And then only really over the last few hundred million years has oxygen increased to the levels we have today. So for most of Earth history, there was much, much less oxygen in the atmosphere than there is today.
Mm-hmm. And what were the main steps that had to be taken in evolution to get from the first unicellular organisms to animals?
Yeah, well, there's a lot of them, as you might guess, but the big ones, I think, first, I think it's fair to say that the first organisms, and in some ways still the dominant organisms on this planet, are what scientists sometimes call prokaryotic, that is bacteria and their cousins, the archaea. They're very simple cells. They don't have a membrane-bounded nucleus. They have limited ability for the cells to shape and reshape themselves in complex ways. Now, I will still say that even on today's Earth, for every kilogram of animals, there's 30 kilograms of bacteria. So, we like to think that we live in an animal-dominated planet, but that's just because we don't see what's going on. In fact, there's as many bacterial cells in your body as there are human cells, which is something that makes people squeamish, but it's what we need them. So the one of the big things is the formation or the origination of the types of cells that make up our animals' bodies. They're called eukaryotic cells. They have a membrane-bounded nucleus. They have many of the functions of energy are in things called organelles, that is membrane-bounded parts of the cell. And again, that's been a big question for decades. There is some movement in recent years because I mentioned that in addition to bacteria, there's another prokaryotic group of organisms called archaea, which were only discovered in 1977. And about 7 years ago, a Scandinavian team of scientists discovered, really by just sampling genomes, they were not collecting and making pure cultures of these things, they discovered a whole new group of archaea, which in terms of a lot of its cell biology is very similar to what we see in the cell biology of eukaryotes. So I think the broad way that people think about the origin of eukaryotic cells now is that some member of this group of archaea entered into a intimate relationship with a bacterium, we'll call a mitochondrion in a cell today. And that gave rise to the last common ancestor of eukaryotic cells. And then that diversified into the many, many different forms we have today. And in about 6 of those branches of the eukaryotic tree, we have fairly complex multicellularity. That is, when 2 cells divide, they don't separate, but make a multicellular structure. And through time, that multicellular structure becomes the unit of natural selection rather than the cells that make it up. Again, we have a lot of intermediates in that process that we can still see today. So I think in general, people are happy with how that happens. And, in some ways, animals are this group that evolved the capacity basically to use its own functions to feed on other organisms. In some ways, animals and fungi are both multicellular organisms that feed on other organisms, but they do it in very different ways. And so only about 700 million years ago or so do we think animals first started to diversify. And only in rocks that are about 575 million years old do we see unambiguous fossils of animals. And even as I say it, I realize that your viewers are going to say, well, 575 million years ago, that's a long time ago. And it is, but it's 85% of the way through the known geologic record. So in terms of the total planet lifetime, animals are relatively recent additions.
Mm-hmm. And when did animals and plants colonize land?
Well, a little bit later. The first evidence we have of plants, anything more than simple algae, things like this, that is the forerunners of the complex land plants we see today, is about 450 million years ago. Things that would be similar to more similar to mosses and liverworts and those kind of simple organisms than, say, a lily or a pine tree. And then what we see is that as plants start to reshape the surface of the land, different animal groups evolve the capacity to live in those environments and take advantage of them. And there's at least 10 different groups of animals have colonized the land from aquatic ancestors. The ones that are most important are, first of all, fungi. Much of the productivity that we see today in a forest is due to fungi that live in intimate association with plants. And then, of course, arthropods, which gave rise to insects, which are 85% of all species of animals are insects, and vertebrates, which gave rise to all of us, are particularly important and successful colonists of land.
Mm-hmm. And of course, when we talk about evolution and evolutionary history, there's also the big extinction. So what were these and what sort of impact did they have on evolution? I mean, did they change the direction of evolution for species in general, of animals, plants, and others?
Absolutely. I mean, I've for many years told my students that mass extinction plays as big a role in shaping the biology you see around you today. It plays as big a role as genetics does. So it is important. And just to back up, we know through paleontological study of the last 500 million years that there have been 5 times in our planet's history when much of the diversity of animals collapses on a short time scale. This is what we call mass extinctions. They don't all have the same cause. The most famous one happened 66 million years ago, wiped out the dinosaurs and lots of other less evocative creatures. And that, it clearly occurs at the time of a massive meteorite impact. And so I think while there's still some debate as to whether volcanism could have played a role in this, I think it's pretty clear that the reason we had this catastrophe 66 million years ago is because this, 11-kilometer impactor whacked into what's now the Yucatan, and the massive environmental disruption. And, in some ways, just to look at our own case, mammals existed alongside dinosaurs for about 180 million years, but there are all these small things living in trees or burrows and feeding at night. And within 10 million years of the demise of dinosaurs, or at least all dinosaurs other than birds, um, all the modern orders of animals differentiated. So our mammal-rich world that we see today is in some ways a direct consequence of that mass extinction. Um, the other extinction worth talking about here is the largest mass extinction that we know of, which happened a little more than 250 million years at the end of the Permian period. And again, that just, you look at reefs, marine ecosystems of before that event, and they're totally different from what we see afterward, and which the things that evolve in their place are more similar to what we see today. And in that case, it's pretty clear that the cause of the extinction was volcanism a million times greater than anything ever witnessed by humans, something called the Siberian traps. And the reason that's important is you say, well, why would volcanism disrupt ecosystems? And with all of this volcanic activity, you have a massive increase in CO2 in the atmosphere that causes global warming. In the oceans, pH goes down, what's called ocean acidification. For various reasons, there is a loss of oxygen in seawater. In other words, what happened and killed something like 90% of all marine animal species 250 million years ago is more or less exactly what's happening today, only this time it's us and not volcanoes that are the cause.
Mhm. And what is the best estimate we have now for the appearance of Homo sapiens?
Okay, well, Homo sapiens, that is, in the very strictest sense, our own modern species. The earliest evidence for that is some bones found in 300,000-year-old rocks in Morocco. There's evidence of close relatives that still have the genus Homo, but are not Homo sapiens, that go back more than 2 million years. But it's really, the world that we understand, and it doesn't even come in 300,000 years ago. Something happens on the origin of 40 to 50,000 years ago when, that's when there's this massive migration of modern humans out of Africa and go all over Eurasia and Europe. We start seeing a new level of culture. I think it's fair to say that our cousins, the Neanderthals, did have some kind of culture, but in 45,000-year-old caves from Indonesia, you see real art. And clearly there's almost sort of a sense of spiritualism in this art. You see, big improvements in tool technology. One might guess that language is coming online here. And again, I think, exactly what happens is very difficult to know. And as you can imagine, it's hard to infer the origin of language from fossils. But clearly, humans evolved this ability to cooperate and communicate in a way that was unprecedented, I think, for life. And eventually, that would give rise to agricultural humans, which changed the world. And very recently, it gave rise to technological humans who could use energy from the earth rather than just energy from muscles. And that, again, is, as we speak, changing the earth in a major way.
Mhm. And how long ago in our evolutionary history, and now I'm talking specifically about Homo sapiens, did we start impacting climate?
Well, people who have looked into this suggest that there's some impact very early on. I was saying that, we clearly have modern humans in Europe 40 or 50,000 years ago. And one of the things that those humans learned to do fairly early was to use fire
Mhm.
as they were hunting. And so there is some evidence that there's a big increase in fires, fires, uh, which would change the composition of species in grasslands and things like this fairly early on. And certainly, um, if you come forward, there is evidence that through hunting and fishing, humans are changing landscapes and seascapes around them well before industrially modern humans came in. But to be honest, even though all of those things happen, what really makes humans change the world are things that have happened largely in the last 200 years with, the use of fossil fuels. And in some ways, it has to be said that in many ways we live in the golden age of humanity. I mean, the idea that I could get on an airplane and see you 6 hours from now, to someone living in 1800, that would have seemed a fantasy. And it was at the time. The idea that smallpox, which was, one of the major sources of death for thousands of years, would be eliminated, would have been a fantasy. So, in many ways, we have evolved the agricultural capacity to feed huge populations. And all of these things together have taken us from a population of humans that might have been a couple hundred million, in 1800, and we're told that we've just passed 8 billion, within the last year or so. So those 8 billion people have huge demands for resources. And of course, it's all unequal. If you live in Europe or North America or Japan or the Middle East, we use on a per person basis huge amounts of resources, more than the earth can sustain, to be honest. Whereas there are less developed countries, let's say in Africa, where people have a very small footprint on the environment. But of course, those people legitimately would like to improve their standard of living, and that will probably make them use more resources too. So, all of this has happened, or at least really accelerated in the last 200 years, and it has resulted in a planet that is totally dominated by humans. At least half of the habitable area of the land surface of our planet is now devoted to agriculture or grazing. Um, Populations of many different species are declining. I know there are a lot of people who think that it's, how can humans exert an impact on the planet similar to that of say, a volcano? But, if you take all of the CO2 emitted by all the volcanoes and hydrothermal events on Earth each year, humans emit about 100 times as much. So we have become, pretty much in the lifetimes of ancestors you might be able to trace back to, a formidable force on the planet.
Mhm. So we are now living through the Anthropocene, right?
Yeah, that's a term which just means the age of humans, and a lot of people like that term because it suggests that in the age of humans, the Earth is fundamentally different. Um, just as the Mesozoic, the age of dinosaurs, was different, the Paleozoic, the age of trilobites. And I'm in sympathy with that. There's been an effort to try and define the Anthropocene as a formal division of the geologic timescale, and that's still ongoing. But however you choose to define it, there's no question that we are living in an unusual interval of Earth history, and the predominant reason why this interval is geologically unusual is because of technological humans.
Mhm. And what do you think could be the worst possible consequences for the Earth and specifically for life?
Well, I think the worst thing that can happen, and I have some confidence that we won't get there, would be a mass extinction of the magnitude of some of the things we've seen in the past. That's not impossible. On the other hand, I think just in the last few years, I get a sense that not only government, but people on the streets really want to change things to avoid the worst consequences. So I think what's more likely to happen is that increasingly over the next few decades, we will see the kind of extreme weather that we have seen in the last 5 years. Everyone says, "Oh, this kind of heat wave is, it's only happened once in every 100 years," but that may tell you something about the past, but it tells you nothing about the future. And I think that, just reading today, that as glaciers are drying up in the Alps, those glaciers have been the sources of water for places like the Po Valley in Italy for millennia, and that has real consequences as those glaciers dry up. We see not only in Western North America, but in Australia and many other parts of the world, drought that increases fires. We see increases in the frequency and magnitude of large storms like hurricanes. So I think that all of that will continue. It does still have to be said that the leading cause of death, it is thought, of humans on this planet is actually air pollution. And you might not think that if you live in Europe or North America, but if you live in India, you'd have no trouble believing that. And so I think that there is reason to think that, without concentrated efforts by people in many countries, and I do agree that people in developed countries have, a greater responsibility here, that there will be, increasing problems for natural populations. That even today, something like 70% of all marine commercial fishery areas are at or beyond their capacity to be sustained. So the diversity that we see around us is in some peril. Our ability to feed ourselves is potentially in some peril as water availability and things like that change. So, if we don't get on the stick, the world that your grandchildren live in will have pressures on it that are much greater than what we experience today.
Mm-hmm. Just one last question then. With what we know now about geology, chemistry, biology, and so on, is it possible to predict the Earth's future in terms of, for example, how the landscapes will change, how life will evolve, how the atmosphere will change, and so on?
Yeah, I'm blanking on who said it now. I'll try to think of it. It said that, prediction is difficult, especially about the future. And that's true. There's things we don't know. On the other hand, I think if we define the future as the next 100 years, then I think, as I said in just a few minutes ago, there are a lot of things that we are fairly sure are going to happen. Storms will increase in intensity and abundance. Drought will increase in some areas. Things like this. It will get warmer. And so I, to the extent that people trying to model our sort of short-term future have been wrong over the last 30 years, it's that they have underestimated the rate and magnitude of change. So I think we have an ability to predict the future. And I should say that if you've ever read Charles Dickens' famous story called A Christmas Carol, he meets with the ghost of Christmas yet to come. And the ghost of Christmas yet to come doesn't say, "Scrooge, this is your future." it says, Scrooge, if you don't change your ways, this will be your future. And I think that's what the models are telling us. And if we are smart and caring and work very hard, we can probably avoid the worst of those future conditions. But if we just sit around with our hands underneath our butts, we're going to be in trouble.
So the book is again a brief history of Earth, 4 billion years in 8 chapters. I will be leaving a link to it in the description box of the interview. Dr. Knoll, just before we go, would you like to tell people where they can find you and your work on the internet?
Okay, well, someone once characterized me as being eminently Googleable. So if you just put Andrew Knoll Harvard in, you can get lots of things. If you're interested in biography, actually Wikipedia is pretty good. I'm the world's worst website person. So if you go looking for this website where I tell you all about myself, you really won't find much. But Wikipedia is pretty good. There's something called Google Scholar, which is pretty good for showing what professional works scientists are doing and who's citing them. So all those things are available. There's a bunch of YouTube videos that I've done in over recent years, and so if someone's crazy enough to want to know more, there's places they can find it.
Great. So, Dr. Knoll, thank you again so much for taking the time to come on the show, and it's been a real pleasure to talk to you.
Thank you, Ricardo. The pleasure's mine.
Hi, guys. Thank you for watching this interview until the end. If you like what I'm doing and to keep the channel sustainable, please consider supporting me on Patreon or PayPal. All of the links are in the description box of this interview. Otherwise, and if you like what I'm doing, please share it, leave a like, and hit the subscription button. This show is brought to you by Enlights, Learning and Development Done Differently. Check the website at enlights.com. I would also like to give a huge thank you to my main patrons and PayPal supporters, Karen Litska and Blanchett Perga Larson, Lau Guerrero, Francis Ford, Hans Frederick Sunder, Ricardo Vladimiro, Craig Healy, Adam Castle, Olaf Alex, Jonathan Wiesel, Jacob Klinkby, Matthew Whittingbird, Arno Wolf, Tim Hollis, Ian Ricalania, John Connors, Paulina Barron, Philip Force Connolly, Jerry Mueller, Herbert Gintis, Rutger Voss, Wo Weingard, Rebecca Newberger, Goldstein, Dan Demetrio, Robert Windiger, Rui Narcio, Arthur Coe, Zup, Marco Neves, Colin Holbrook, Susan Pinker, Bernardo Seixas, Pablo Santurbano, Simon Columbus, Jorge Espinha, Phil Kavanagh, Corey Clark, Mark Blythe, Roberto Enguanzo, Michael Stormir, Eric Neumann, Samuel Andreev, Tiago Nunes, Bernardini, Alexander Dunbauer, Fergal Cusson, Ivan Bodrenko, Paul Herzog, Don Ross, Jonathan Librant, Haslem Bullitt, Nathan Nguyen, Stanton T., Samuel Correa, Eric Hines, Mark Smith, J.W. João Eira, Tom Hummel, David Sloan Wilson, Yacila Deja Araújo, Romain Roach, Dmitry Grigoriev, Diego Londoño Correa, Tom Roth, Yannick Punter, Adana Rusmani, Charlotte Bliss, Nicole Barbaro, Adam Hunt, Pavel Ostazewski, Nelek Bach, Catherine and Patrick Tobin, Al Ortiz, Guy Madison, Gary G. Hellman, João Linhares, Lida Cosmides, Saima Afzal, Adrian Yagi, Nick Golden, Paulo Tolentino, João Barbosa, Jules Price, Edward Hall, Edin Bronner, Franca Bortolotti, Gabriel Pons Cortez, Ursula Litzke, Dennis Cook, Scott, Zachary Fish, Tim Duffy, Todd Shackelford, Sunny Smith, and John Wiseman. My producers Cesar Webb, Jim Frank, Lucas Stafiniak, Luis Caetano, Tom Wagner, Curtis Dixon, João Linhares, Benedict Mueller, Vega Guidi, Sardus France, Thomas Trumbull, and Nuno Welder, and my executive producers Michel Rugieski, Rosie, James Pratt, Matthew Lavender, Sergio Codriano, and Bogdan Kanivets. Thank you for all.